Yeah. How many lines?
Is it QV multiply V or XV?
Multiply, but it's a special multiply. That multiply means you must use your left hand for the direction. Yeah?
Use my left hand for the direction?
Yeah. That F, in the way look, listen carefully. That F, no, look at me. That F is this F on your thumb. So that formula says this F is equal to QVB, and the direction, you find it using your left hand. That's what that special multiply means. Oh, you look so confused. I'll give you an example. When something is moving in a circle, you have the formula for the force, don't you? When it's moving in a circle, mv squared over r. And the other formula? Do you remember? M omega squared r. Right? What's the direction of that force? To the center. That formula there also has a direction. The direction you find by using your left hand. Just like with the circle, it has a direction. Yeah? Hot dog?
Nothing.
Sad. You watched the video?
Yeah.
It was okay?
Yeah.
Just those few questions?
Yeah.
Good.
And I don't know how to do the homework.
That's okay. You can watch the new video. Okay.
It isn't uploaded to Moodle. It's
Oh.
on your...
No, I don't. It's only on YouTube. I'm not uploading to Moodle because in September we're going to delete that Moodle and make a new Moodle. A better Moodle. Ones that work on your phone. I know. But too bad you will be gone then.
Should we download the application?
Download what?
Download the application. The name is Moodle and open this go to Moodle.
Not necessary. Okay. Next lesson. Hot chocolate? With cream?
No.
No. Americano with salt and salt and pepper and hot chocolate?
No.
Americano?
No.
Cappuccino?
No.
Latte?
Yes.
No. So you like milk?
Everything.
Oh, good. Got this? Oh my goodness. How many sugars? Okay, alright, don't tell me. I don't want to know actually. Alright, did you write this down? Current carrying conductor in a magnetic field. Okay. So this is just a revision of the left-hand rule. So for example, here's north and here's south. So if I look at with my hand, the current is going right, the magnet is going in, so the force is going up, like in the picture. Yeah? Is that okay? Yes? So, remember that a charge moving in a magnetic field will experience a force. What about a current? Remember, a current is the same as a charge, but just with a time. So let's find a formula for the F. Let us see. So, for example, here is north, here is south. Here's the magnetic field, so I'll call that B. Here is the current here, so I'll call that I. And we'll say it has a length is L. Right, so you know that F equals QVB. And you can imagine that there's lots of little Q's moving along here. These are all little Q's. So we need a formula that doesn't use Q. We need a formula that uses I. And you remember, but I know that Q equals IT. Maybe you remember that from electricity. So what you can do is put that in here. So F equals ITV over B. But then, if you remember your triangle, distance, speed, and time, you know that speed is distance over time. So this can be written as ITL over T times B. They cancel, leaving you with the easy to remember formula, Bill. Yeah? So this is the force on a current in a magnetic field. Did you all hear that? This is the force on a current in a magnetic field. Okay. So we have F equals Bill. In this formula, the current is perpendicular to the field. If it was not perpendicular, that is, if it was an angle theta, then let's see what the formula is now. So I'll just change this a little bit. I'll just make, instead of being perpendicular, I'll put it at an angle now. So if I just draw it again, make it nice and clear. This is the north and this is the south. So let's say our current I is going across at an angle. It has two parts. This one and this one. So this is I cos theta and this one here is I sin theta. If, of course, the theta is here, which I think is what abort! I have the theta the wrong way. I'm sorry, we usually measure the theta from here. So that's going to change this to a cos and the other one to a sine. All fixed. Now, before I continue with this, let me just go to the side for one moment. Let's say I have my magnetic field going like this, and let's say I have my current also going like this. If I use the left hand, so, I need some colours. My current is going this way, and my magnetic field is also going up. There's this problem. If you look, this is the magnetic field. Which way is the magnetic field going? Up. This one's the current. Which way is the current going? It's going up.
Current.
This is current.
Yeah.
Yeah. Current is going up also. So what do I do? The force is field is going up, the current is going up. I can't do it. In fact, there's no force here. If the current and the magnet are the same direction, there's no force. So in fact, there's no force here.
Current and what?
Magnetic field. Yeah. Okay, back here. So you can see that when it's at an angle, this force here is zero. There's no force. No force. So we actually only care about this one, which is perpendicular. So it means our formula will be F equals BIL sine theta. That's all. Yeah. Continue? Continue? Yes, okay. Right. BIL sine theta. Right. If a force acts on a current in a magnetic field, then could we use this force to do some work? Yes, we can. So here's how you could do it. Let me explain. So if you watch, here is the current. Current comes out here, goes around, and then it goes around here, around here, around here, around here, and then back to here. Okay, so this is the current. So here, which the current is going in, and which way is the magnet going? To the left. So which way is the force going? Up. So there's a force up here. Likewise, when you do it on the other side, you get a force going down. So what will happen? This will go up, this will go down, and then this will spin. So you just made a motor. This will start to spin. So we don't have it, but you know the electric fan? We don't have it here. You know the fan? And like electric car or the Lewis, any electrical spinning like this, that's how you do it. You need a magnet and a current, and that's all, and you can make it spin. Now, just note, there's a gap here. These are special brushes that touch the wheel. And you realize that you can't stick it to the wheel, because if you did have it stuck to the wheel, when the wheel turns, then the wires will tangle, you know, like it's hard to do, but I mean, if you had the wire, the two wires stuck to the wheel, then as it turns, the wire will twist. So in fact, this is like a brush. The brush is just touching the wheel. So as the wheel turns, it doesn't move. Yeah. So this can keep turning around, and this doesn't move. This is a brush. Usually like a carbon brush. There's a small gap here, so that the current doesn't go this way. You want the current to go around here. So there's a gap, not touching. Okay. This is called the commutator. These are called the brushes. And this here that turns is called the armature. Now I'm very sorry to tell you this, but sometimes in the exam they ask you to draw this. So please draw a beautiful picture of this. I know, it's terrible. So this is called a DC motor, direct current motor. Okay, did you draw this?
Remember all of the cross language.
Yep. Yeah.
Where's the blue one?
Magnetic field. Yep. Commutator or commuter. Commuter. You know, I think you're right, Sophie. Commutator. But I think a lot of people say commuter. But maybe that's wrong. Maybe people should really say commutator.
2M.
2 M's, yeah. Commutator. That's better. Native speakers can be very bad with pronouncing words. Oh, ugly.
Batman.
It looks like something that would kill Batman. Yes.
No.
No. Batman could be trapped on it as he turns around. No? Alright.
Is this one very long and didn't fall down?
Which one? The commutator.
Yes.
Very long. No.
Is it on there?
Yeah.
And it didn't fall down?
Fall down. Why?
Because it's not sticky on the...
Oh, the wire is not stuck here, but maybe this is stuck to something that's turning, like a wheel. Yeah, no, this doesn't fall down. Don't have it here. Like, try and draw it. Like, for example, if it was a car, here's the wheel, and it'll be stuck on the wheel like this, you know? Ugly, 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 ugly. Yeah. Yeah, no, neither can I. No, it doesn't fall down because it is stuck to like a wheel. It is stuck to something. Just the wire is not stuck to it. Okay. Let's find a formula here. For the, do you remember what the torque is? No. No. Soggy? Are you sure? Have a guess. Something balanced, yeah. What? The torque, in case you forgot, which you did, the torque equals the turning force. Yeah? So what I'm going to do, I'm going to look at this, I'm going to look at this rectangle here. I'm going to look at this rectangle here. So this will be or, this will be or, and this will be L. And you understand I call this or because it's turning in a circle. It's a radius. This is turning a wheel. Here, or will be from here to here. This will be stuck to a wheel or something. So there are two forces, one up here and one down here. So the turning force will be F or plus F or. They're both clockwise. The blue is the force, the F. We're getting there. So this is equal to 2F4. But what's the formula for F? No, the one from today. F is Bill. So if you want, that's IB 2 or multiply L, like this. Now, can anyone tell me what 2 or multiply L is on the picture? Here is 2 or, and here is L. What'd you say, Amanda? Very good. That is actually the same as the area. So this equals IBA. One last thing here. This formula is if you have one wire. But you can make more force if you have more than one. If you have like 2 or maybe 3. 3 loops. The wire goes around 3 times. You can make 3 more currents. Makes 3 more forces. So we usually put an N here, where N is the number of loops. So you get this formula. The turning force, the torque, equals IBAN.
A is area
Yeah,
of what?
the rectangle.
Of the IBA.
N, yeah. Yeah? Continue? Okay. So we have torque, which I used this symbol last year. I use an L, it doesn't matter. Torque is IBAN. Right. So do you remember that flux is the number of magnetic field lines? However, imagine now that the field passes through n identical regions we're interested in. Let's find the total flux. So, for example here, if I have 1, 2, 3 lines here, then the flux would be 3 Webers. Okay? But sometimes what you can have is something like this. Maybe you have 1, 2, 3 like this. So the total flux, that would be, or let's make it 4. And if I have 3 lines, the total flux would be 4 times 3 Webers, because there's 4 areas. So in other words, the total flux would be N times the flux for one area. So just multiply by N if you have N areas. This is the total flux, but it has a special name. It's called the flux linkage. It means total flux. Also remember that flux density is flux over A. So another way to write this formula will be NBA. Linkage. Linkage, yeah. It means total. Continue?
No.
Okay. here's the formula here. So total flux is what I just wrote. They're the two formulas. Yeah. Now, if the field makes an angle theta with the normal of the region of the space, then, so this time, let's draw the space again. But it's not perpendicular, now it's at an angle. So you have two parts. The part that is perpendicular and the part that's not perpendicular. Maybe I should draw this in a different perspective. So let me just draw that again. So let's say that the direction for the field, there's 1 Weber, is at an angle. So we care about this one, but we don't care about this one because it doesn't go through the area. And here this is theta. So this will be, if I call this B, this will be B cos theta. Yeah. So, I mean, the formula just becomes this now, with a cos theta in it. To my beautiful picture. There we go. This here is the area. The magnetic field is going through the area. Originally, Grace, I originally drew it like this, with the magnetic field going in, but now I'm drawing it from I'm looking at the side. So I'm looking here. So in my first picture, I was looking at it like this, but I thought that was difficult, so I'm looking at it like this, on the side. Okay. Yeah? Now back to my text. Which word? It's only for physics. Yeah. Okay, continue? No. Continue now? Okay. Our first question. can write this down. Yeah, okay, let's have a look here. So what you have here, you have 2 amps and the length is 20 centimeters, and there's a magnet here going through of 3 Tesla. So the force is equal to Bill 3 times 0.2 times 3 times 2 times 0.2. What's that? 6 times 0.2. What's that? 1.16? 1.16? Is it? 1.2, is it?
Yeah.
1.2 newtons. Tesla. And then the next part is if it's at an angle. What did I say the angle was?
80.
80. Okay. 80 with field. So 80 this way. Yeah. So we get then F equals BIL sine theta, isn't it? Wasn't that our first formula? Sine theta? Yeah, so this would be .18 newtons. Yeah. Yeah? Okay. Next now. Okay, this one please. I did. My other shoes were getting too old. And my feet, the boots were too heavy. I needed something lighter. You know what I mean?
Yes.
You like them? Only 25 euros.
Looks good.
Yeah, I think so. It's comfortable, like slippers. Maybe I should have got ones like what everybody has with the air bubble. You don't have the air bubble.
Yeah, yeah. Sports shoes.
Yeah. Or maybe I should have got the one with the lights.
Yeah.
You know the ones with the red lights? You know those shoes? The one with the red lights. Ah, you do. Yeah, exactly.
Why?
Be funny.
Working in the dark.
Exactly.
Everybody can see.
Yeah, exactly, yeah.
Not light in the dark.
Yeah.
If they ask to draw the DC motor, and you need like which part is which part.
Yes. Yeah. So a DC motor is used to turn a wheel. You have 3 amps and 5 Tesla and 1,000 turns and a square of length 20. So this here is 20 centimeters and there's a force up and there's a force down and it's turning, of course. And the formula for the turning force is IBAN. What's the I in this question, please? What's the I? The current? 3. The B? 5 Tesla? The area is 0.20 squared because I said it's a square. And the N is 1,000. Does anyone remember the unit for turning force? Newton meter, yeah. Yeah? Okay. last example, I think. Yeah.
What is iron rod?
Iron rod is like an iron bar, like a circular piece of iron. Like, where would you see an iron rod? Like in a building, maybe. Oh, here, it's like this. This is like an iron rod. This is a rod shape. It's like a circle and it's long. It's circular base, yeah, for a rod. Okay, you got that one? Not yet. What are we waiting for? Waiting for Grace. Yep. Right. So what you have here, you have an iron rod and you have this is wrapped around whatever. I think I said 100. Was it 100 times? And there's a magnetic field going through this way of how much? 2 Tesla? 2 Tesla? And lastly, I tell you what the radius is here. What is it? 5 centimeters. Yeah. So the flux linkage, oh my pen, there we go. The total flux linkage is equal to NBA. Now the N is 100, the B is 2, and the area is pi r squared. Pi over 2, 1.57 Webers. Yeah. Yeah? Okay. Next is if it's at 10 degrees. So if it's the angle is slightly different, if it's just moved by 10 degrees. Come on. Oh, here we go. If it's at an angle now instead of 10 degrees, so the only difference is then you would have to put in a 1.57 cos 10. So you would get 1.55 Webers.
Why is
Isn't here because you only care about this part, you don't care about this one. So this is the cos and this is the sine, and this is the 10.
How to identify which part is sine and which part is cosine?
Cos is the one that touches the angle.
No.
Yeah. Okay.
So I did a big thing.
I made a stupid mistake. You made a stupid mistake.
Homework 2
Yeah.
is not 10 Tesla, it's 1,000.
Ah. Okay.
Sorry.
When you watch the video for the homework, the answer for 2 might be wrong. It's 10. It's 1,000,
Yeah,
not 10.
1,000.
Right. So the answer is too small. Okay. Continue. All right. So here's the homework for this one. Did you get it? Yeah? Yeah?
The last question.
Yeah?
The magnetic field.
Yeah?
You draw the picture. Can I see your picture?
Yeah.
Yeah, the magnetic field is maybe this way, and your cosine is the same one. So maybe it's no force on the
The magnetic field
yeah.
in this question goes through the rod. Yeah.
But cosine is the same way, so maybe it's calculate sine.
No, I know what you're thinking. Yeah, because you're thinking cos is the same as the magnet,
Yeah.
so it should be different. No, and what we're looking at is how many Webers go through the rod. So the magnet is perpendicular to the face of the rod. So this one is parallel to the face, so we don't care about this one. We only care about this one because it's perpendicular to the rod. I know why you're thinking that, because the magnet is going this way, but that's for force. There's no so there'll be no force in this direction with the magnet. You're right, but that's not what we're doing here. Okay. Can I close this? Yes?